Okay, ladies and gentlemen, we're going to be talking about Chapter 13 tonight, and this is solutions. And we've kind of hinted at a lot of this stuff when we talked about Chapter 11. We're going to formally talk about it. And so what we have, and we should probably do a real quick definition to start off with of what a solution is. And a solution is going to basically consist of two parts. You're going to have a solvent, and you're going to have a solute. Your solvent is present in the largest amount, and the solute is the dissolved particles in the smaller amount. And we've talked about this a little bit before. Solvents for us mostly, not always, but are mostly water. And solutes are the things that we put in water to dissolve. And for example, we can dissolve sodium chloride in water. We all know this. And the equation, if we were to write sodium chloride dissolving in water, we would write NaCl solid plus water as our liquid. And then over here as a product, we're just going to have sodium ions in an aqueous format, and then we're going to have chloride ions, also aqueous. And that's the aqueous, once again, tells us that's what's going on with the water. Type of intermolecular force that we have going on here, of course, we're going to have ion, which comes from the ions of the sodium and the chloride, and we have dipole, which are the dipole on the water molecules. And really what's going on is the attractive force between the ion, being sodium or chloride, and the dipole in the water is stronger than the attractive force between the ion and the ion. And so water can overcome that force that holds a sodium and a chloride together, and this guy's going to dissolve. And this gives you an idea of hydration. What's going on here is when a solvent is dissolving in water, we call it hydration. And so just to give you an idea here, like let's say right here, there is our water molecule. And you notice they've got this molecule labeled negative, and that would be on the oxygen, and positive on the hydrogens. And the reason for that is, as we know, oxygen has a greater electronegativity. It's going to attract those electrons towards it. It's going to have a slightly negative pole. The way this illustration looks is it's really, it's not super negative, it's just slightly negative, but there's going to be this force of attraction. So what happens is, down in here you have, I'm going to kind of circle, this is our crystal of salt repeating positive sodiums and negative chlorides. There's our crystal. And they've got this interaction. They're holding them together, you know, and with this lattice energy. And what's happening is the water molecules are coming in and orienting themselves so that they can surround the water molecule. So let's take a look at this chloride up here in the left-hand corner. Here he is, this negatively charged chloride. And notice the positive hydrogens are all closer. They orient themselves so that they can surround that water molecule. Once again, we're calling this hydration. And then if you look at a negative, let's say here's our negative our negative sodium. I'm sorry, it's a positive sodium. It's being attracted. The oxygens on the water molecules are being attracted to that, and they're going to just start surrounding it, just like we see, you know, kind of over here. We have all these water molecules surrounding the sodium, and all the oxygens are sort of pointing towards that sodium because it's positive. Okay, that's hydration. That's really the process that's going on. So you should be able to kind of visualize this and draw this if you're asked to do so. A couple things else that I want to just talk about really quickly. If we do put something in water, we know that sometimes it's going to be endothermic and sometimes it's going to be exothermic. And really what's going on there is whether or not it's exothermic or endothermic really depends upon the amount of energy it takes to break apart the ions, the amount of energy it takes to move apart the water molecules, and the overall energy that there's going on with the interactions. Sometimes endothermic to absorb heat, it's going to feel cold if we touch it. Sometimes exothermic, like a hot pack, it's going to give off heat, feel hot when we touch it. Okay. A couple other things that we might come across when we're dealing with solutions is we might come across something that's called a hydrate. And this is an example of a hydrate right here. And usually hydrates are solids. And this is nickel 2 chloride. And usually you'll see a dot in the middle right here, or a star. Usually it's a dot. I couldn't make a dot on the computer, so I made a star. And then 6 waters. And essentially what this means is you have a nickel 2 chloride surrounded by 6 waters within a crystal that's what's called a hydrate. And the way we name these guys, it's just so you're familiar, and is we name these guys, you know, obviously nickel 2 chloride. But we also name that 6 on the water, how many waters. It's not always 6, it could be any number of waters, anything 1 to a bunch of them. And we use those old, like we'll use hexa hydrate. Then hexa is telling us there's 6 there. And if we were to calculate the molar mass of nickel 2 chloride hexahydrate, we would have to add in 6 water. So it would be 6 times 18. We would add that into the mass of whatever nickel 2 chloride is. So if we have to deal with that within a stoichiometry problem, that's what we have to remember to do, is just add in. And a lot of students make the mistake is they see that dot there in the middle and they multiply in 6 waters. Don't do that, just add them in. Okay? Okay, we're moving on to section 13.2, and once again, it'd be a good idea to read these sections in the book. Saturated solutions and solubility. And so let's talk about this. This is some general chem stuff, though, but we'll remind it. So this is a little equation right here, and if we have a solute plus a solvent, we can produce a solution. And it also has something really important. It's got a double arrow right there, and it means this is reversible. And we'll be talking, in great detail very soon about reversible reactions and equilibrium and things like that. So we talked about the forward direction. And on the forward direction, which is defined as going from right, from the solute and solvent, to left. And I think I typed that wrong. It really is left to right. I'm going to have to change that right now. Okay, I fixed it. So now forward direction is going to be left to right. So this is our forward direction here. Forward direction, left to right. And that's going to be called solvation. Solvation. And this is our solution process. This is taking a solvent and a solute, mixing them together, and producing a solution. Okay. Now we can also have our reverse direction, which is right to left. We can make this go the other way, and this is crystallization. Crystallization. It's our left. Now, we can form a dynamic equilibrium. And so let's talk about what is a dynamic equilibrium, because this is really a really important idea. Let's say we take a beaker of water. That's my beaker of water. And into this beaker of water, we dump in something that we're going to want to dissolve. Let's say we're going to throw in here some potassium chloride. And we should know that potassium, an alkali metal, is going to be soluble in water. So we stick this in here. And so let's say we put a little tiny bit in here, maybe just a couple grams or something like that. And what's going to happen is, like we said before, those water molecules are going to start surrounding, and the potassium is going to go up into solution, and then we're going to have our chlorides going up into solution until there's nothing left at the bottom of the beaker. Everything dissolves and everything is good. Okay. Now let's give another scenario here, and another beaker of water. We throw some of the same substance in there, KCl solid, potassium chloride, and let's say we put in enough there that not everything dissolves. We have ionization occurring, but we also have crystallization occurring at the same rate. And once this occurs, then we have the same rate, how fast ions are being formed and how fast ions are coming back together to form a solid. If we have the same rate of the forward and the reverse reaction, we have an equilibrium occurring. Same rate as an equilibrium, a dynamic equilibrium. Same rate going forward and backwards. And obviously it's not going to occur with just two ions. There's going to be tons and tons of ions, moles and moles of ions, of course, depending on the substance. And each substance has a different, what we call, solubility. Okay. Now, this first example that I gave over here, this was an example that, I'm sorry. Sorry, we'll have to back that up. A solution that's in an equilibrium with an undissolved solid is just what we said right here, and obviously that's going to be at equilibrium. We also call this solution that's at equilibrium with some undissolved solids saturated. And that's the important word. A saturated solution has some undissolved solid in the bottom of it, and there's continual ionization and crystallization, occurring. Okay. The amount of solute needed to form a saturated solution is, in a given quantity, is what we call solubility. And so different substances have different solubilities. It's how much solid can dissolve in a given amount of liquid. Solubility is typically measured in grams of solute per 100 milliliters of water. So oftentimes you'll see solubility is given in grams per milliliter of water. An example would be sodium chloride. Now for sodium chloride, the solubility of sodium chloride is about 35.9 grams in 100 milliliters of water. So, and that's at 0 degrees Celsius. Now, one of the things that we need to recognize is typically, but not always, but typically, if you were to increase the temperature of the solvent, you can also increase solubility. And so if we want to increase the solubility of sodium chloride in water, we just have to heat up the water a little bit. And that makes sense. Sugar that's put into iced tea doesn't dissolve as readily as sugar that's put into hot tea. They dissolve at different rates. So that's not a hard and fast rule, though, because sometimes you can increase temperature on certain substances and the solubility goes down. But for the most part, it goes up. Now, let's say you have a capacity to dissolve more solute. So if you are to the max of amount of solute that you can dissolve, we call it saturated solution. You know, we were at that equilibrium. But let's say you were at that first example they gave up there with the potassium chloride. This is going to be unsaturated. So if we want to dissolve more, we call that unsaturated. It still has the capacity to dissolve more. And the next thing is, if you have a solution that holds more than a solubility, because you've heated that solution up, that is typically called supersaturated. Supersaturated. That's a U right there. Okay, and so I'm going to show you a quick little video on a solution called sodium acetate. And sodium acetate, as we know, is NaC2H3O2. Now, sodium acetate dissolves in water very, very readily. I can flip over here to this page, and here's a picture of sodium acetate right here. There's sodium acetate. And if I scroll down, it tells me sodium acetate right there has a solubility of 100 grams or 119 grams in 100 milliliters of water. So this thing's got a fantastic solubility. So flip back over here. Now I'm going to show you a video of a supersaturated solution and what happens to a supersaturated solution when you cool it back down. Okay, so this is a setup, and what they have is 2 Erlenmeyer flasks, one on the left, one on the right, and 2 Petri dishes, one on the left, one on the right. What they've done is they've created a couple supersaturated solutions. They've taken sodium acetate in both of these flasks. They've heated it up really hot. They've dissolved a whole bunch more than 119 grams per 100 mils of water, and then they stuck it in the fridge real carefully and they let it cool down. And this is what's going to happen when they pour it. So they're going to take off a stopper, and they're going to start pouring it into this glass Petri dish, and watch what happens. This is a supersaturated solution. And then we have crystallization occurring. We have that reverse process. We have it going from ions, and they're coming back together. To form a solid. So we have solid sodium acetate crystals being reformed. It's kind of a neat thing, going from a liquid to a solid right before your eyes. And normally this takes quite a while to occur. Now the neat thing is, what they can do is just keep pouring a little bit more on the top and watch what happens. it actually starts growing straight upwards as these form this nice crystalline structure. And in a way, it's sort of how like a stalag might form from the bottom of a cave going upward as water drips down, and inside in the water there's some dissolved solids. Typically that happens. Okay, so they can form a little tower out of that. And this sodium acetate, they like to call this hot ice as well. And the reason why they call it hot ice is because this is an exothermic process. As this crystallization occurs, it just keeps getting hotter and hotter and hotter, releasing heat as these guys recrystallize. They can only go so far before the whole thing just falls over, but kind of neat thing, hot ice. Now the next thing I want to talk about when we're almost done with this video is the factors that affect solubility. We're into 13.3 now, and we've talked about these in class already, and this was a little bit in some of the readings, and so let's talk about this. So first off, we need to know that the stronger the attractions between the solute and the solvent, the greater the solubility. If the attraction between the solute molecules is so great, then something's going to be what we call insoluble. It will not dissolve. There has to be this force of attraction between the solute and the solvent molecules. We also know, and we talked about this in class, that polar liquids tend to dissolve in polar solvents. Water is polar, and polar molecules typically will dissolve in water. And we know polar molecules are polar because they have a dipole. Water, obviously, we've talked about it before. Water has this dipole, this slightly negative charge on the oxygen, slightly positive charge on each hydrogen, because oxygen is electronegative, and it pulls those electrons closer to it. They surround it. And so what we're going to have is we're going to have this force of attraction between that and another polar molecule. Any polar molecule, anybody who is, maybe let's say NH3 or something like that. So maybe you might have this force of attraction that's going on right here. Those type of molecules are going to be attracted. Liquids that mix, we call miscible. You might hear the word miscible. They're mixable liquids. And liquids that don't mix are called immiscible. And there's a good example of an insoluble or immiscible object is, once again, water with hexane. Now, if we were to draw the structure of hexane, we have 6 carbons, just like that, single bonds in between each one of these carbons. And then around every one of these hydrogens, we have, or one of these carbons, we have hydrogens. And so we have a nice symmetrical molecule that is nonpolar. There we go, got all our hydrogens in. Sometimes they like to talk about these as CH3, CH2, 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 CH3, but it's a very nonpolar molecule, and so these guys are immiscible. They're not going to mix, they're not going to dissolve, because one's polar, one's not. We should mention the alcohol groups that occur. For example, methanol, CH3OH. It's going to look like this. And you have some hydrogen bonding going on. And you know there's going to be a force of attraction between these two because, what kind of bonding do you have going on, or what kind of force of attraction you got going there? And you get some more hydrogen bonding going on in that water molecule. So there's going to be a really good force of attraction between methanol, an alcohol group, and this is not a hydroxide. Hydroxide would have a negative on charge. These guys are sharing electrons and covalently. And we talked about this in class, that we have this rule of thumb: likes dissolve likes. Polar molecules like to dissolve in polar molecules, nons and nons, and that's the way it is. We'll talk more about factors affecting solubility, especially with respect to gases, in the next video, which will be another day.